Light is a very interesting natural phenomenon because it can act as a wave or it can act as a particle, and this double nature of light became known as the wave-particle duality of light. So let's begin by describing the wave theory of light. According to Maxwell's theory on electromagnetism, light essentially is an electromagnetic wave that consists of oscillating electric fields and oscillating magnetic fields, as shown in the following diagram. So we have the electric field shown in blue that is oscillating along the y-axis. The magnetic field shown in green is oscillating along the z-axis, which is coming out of the board. And the entire wave is actually propagating along the x-axis. It's moving along the x-axis with the velocity v. So we see that the velocity vector, the electric field vector, and the magnetic field vector are perpendicular with respect to one another. And this is true for any electromagnetic wave. Now, just like a mechanical wave carries energy as it propagates through space, electromagnetic waves also carry energy, and light waves carry energy, and the energy is stored within the oscillating electric and magnetic fields. Now, there are two important experiments that were conducted which basically confirmed the wave theory of light. And these two experiments were the single slit and the double slit experiment. Now, in both experiments, light was essentially directed at either a single opening screen or a double opening screen. And light was observed to diffract and interfere. And that led to the diffraction pattern that consisted of dark and bright fringes. Now, the only way that this diffraction pattern was explained is by assuming that light does in fact act as a wave. Now, let's move on to the particle theory of light, also known as the quantum theory of light. So the quantum theory of light basically states that light consists of discrete particles known as photons that each carry an identical quantity of energy that depends on the frequency of that light. So this is our light wave that consists of individual discrete photons. Now, each photon is in fact a massless particle that is basically a bundle of energy, and the energy is given by taking h and multiplying by f. So the energy that each one of these photons carries can be calculated by taking Planck's constant h and multiplying by the frequency of oscillation of light. Now, two important experiments basically served to confirm and validate the photon theory of light, the quantum theory of light. And these experiments were the photoelectric effect and the Compton effect. So, within the photoelectric experiment, light was essentially directed at a metal surface to eject the electrons found on those surface. Now, if the frequency of light was not high enough, no matter how high the intensity of light was, no electrons were ejected. However, if the frequency was high enough, those electrons were ejected, and increasing the intensity would in fact eject more electrons. However, by increasing the intensity, we do not actually increase the energy that each photon carries, and so the kinetic energy of the electrons did not actually increase. So once again, within the photoelectric effect experiment, light was directed at metal surface, and electrons were only ejected if the frequency of light and the energy of light was high enough. Now, if the frequency was too low, increasing the intensity did nothing to eject the electrons, because by increasing the intensity, we're simply increasing the number of photons, but we're not increasing the energy that each photon carries. So that means no matter how intense our light wave is, if the frequency is not high enough, because of the one-to-one collision between the photon and electron, no ejection takes place. place. However, if the frequency was high enough, increasing the intensity did in fact eject more electrons, but the maximum kinetic energy of each electron remains the same as long as the frequency is constant. So this experiment basically validated the particle theory of light, the fact that light consists of photons. Now, the second experiment that basically validated the photon theory of light was the Compton effect. In this experiment, photons basically collided and interacted with stationary electrons, and scattering of those photons took place. Now, the scattered photon had a larger wavelength than the incident photon, and that basically meant that some of the energy was transferred to those electrons. So this basically confirmed the particle theory of light in a similar way that the photoelectric effect confirmed the particle theory of light. So once again, light can act as a wave or it can act as a particle, as described in these two theories. And this phenomenon, this concept, became known as the wave-particle duality of light.